Hello everyone, we are the team Balamand Civil Engineers number 1 and today we are excited to share our project for the ACI Ecoconcrete student competition. This presentation will include an introduction, decision making, base case scenario, alternative case scenario mix design, performance comparison, life cycle assessment, and finally data visualization. Our goal was to design a concrete mix that not only meets performance standards but also significantly reduces environmental impact. We created two mixes, a base case scenario using only Portland cement and an alternative case scenario where we replaced a percentage of the cement with supplementary cementitious materials. By doing this, we reduced CO2 emissions, improved the durability, and kept the same overall volume material. Throughout the project, we focused on sustainability without compromising strength or constructability, and we are proud of the balance that we have achieved.
When it comes to designing our eco-concrete mix design, decision was an important part of the process. We started by researching various supplementary cementitious materials like slag, silica fume, and analyzing their individual benefits. So, from previous experiences in the lab, we realized that slag was chosen for its durability and resistance to corrosion, while silica fume was used for its ability to significantly reducing permeability and enhancing strength. We applied what we learned in the lab and by doing trials and errors on the Life 365 software, we found out the most effective balance. We balanced between the strength, workability, and sustainability. According to the teamwork, our group also divided the work efficiently. So some of us was focusing on the environmental impact calculations, while others was focusing on the design mix. And we arrived at a mix that not only performs well, but also meets the competition's sustainability criteria. So it was a mix of technical knowledge, teamwork, and hands-on testing that got us to the final design.
Now to talk about the BCS and ACS mix design, let's start with the BCS. This mix followed a traditional concrete design made entirely with 100% ordinary Portland cement as the binder. It also included natural aggregates and water. We have 450 kg per cubic meter cement, 180 water, fine and coarse aggregates 1,833 kg per cubic meter, and high CO2 impact calculated to be 427.5 kilograms CO2 per cubic meter. This is the kind of mix commonly used in industry, but it's also the one with the highest environmental footprint. As we know, cement alone made up a large percentage of the environmental impact, about 75% of total emissions in this mix. So we did the ACS mix design to make the mix more sustainable. We replaced 40% of the cement with two supplementary cementitious materials, 30% slag, which is equal 135 kilogram per cubic meter, and 10% silica fume, equal 45 kilogram per cubic meter. That means the binder in the ACS is only 60% Portland cement, and these materials are industrial byproducts, and they have a much lower carbon footprint compared to cement. Slag is a byproduct from steel manufacturing, and silica fume comes from the production of silicon. By using them, we not only cut emissions, but also reused waste materials.
So what did we actually improve? The biggest win was a reduction in global warming potential from around 427.5 kilograms of CO2 per cubic meter in the BCS to just 277.4 kilograms in the ACS. That's a 16.4% improvement. And on top of that, we maintained similar proportions in volume for fair comparison and ensure the structural integrity of the mix, that it was not compromised. Overall, our simplified LCA showed us that even small changes in material composition, like using industrial byproducts, can lead to significant environmental benefits without sacrificing performance.
So basically, concerning the major factors, several major factors affected our simplified LCA outcome, starting with the type and amount of binder. Since cement has the highest carbon footprint, reducing its percentage significantly impacted the results. We replaced it with slag and silica fume, which are low-emission byproducts, helped lower the global warming potential. Another big factor was the transport distance of materials. Local sourcing can reduce emissions while importing materials increases them. Also, the mixed proportions, especially how much binder, water, and aggregate we use per cubic meter, affected the CO2 total. Finally, even though it's a simplified LCA, functional performance matters too by maintaining strength of our mix.
Regarding the importance of simplified LCA. So the simplified LCA is essential in guiding our material choices because it gives us a clear picture of the environmental footprint of each mix, even before we consider durability. So it also helps us to compare the mixes based on CO2 emissions and resource use, which is crucial when aiming for sustainability. Meanwhile, ACS mix performed or gives us more strength with lower environmental impact. It leads to more eco-friendly and a future-ready mix. Moreover, this tool supports smart decision-making by highlighting how small changes, like reducing cement or using byproducts, can lead to big environmental benefits, pushing us to design not just strong, but a very responsible concrete.
And finally, some data visualization appears as different figures and graphs having different parameters. The first figure here shows us a section of a slab designed using our ACS mix, showing a simulation of chloride ions penetrating into the slab, which remains near the surface, so relatively low for over a period of 47.5 years, indicating high resistance to chloride penetration, and especially since our mix is considered to be in a marine environment. Secondly, the table compares mostly the environmental impact from each mix, clearly showing that the optimized mix emits much less CO2 than the BCS, as mentioned before. And the second table here also compares the cost of the two mixes, showing that ACS mix is slightly more costly to do, but since it's durable, on the long term, it will be more cost effective and sustainable. And thank you for listening.